Okay, so for our two-box question here that now involves friction. So we got these two boxes, they're identical materials, different masses, okay, placed next to each other on this rough surface. An applied force on box A causes both boxes to accelerate at 2.6 meters per second squared to the right. The magnitude of the force of friction on box B is 28.3 newtons. Calculate the force exerted by box B on box A. All right, so looking at this diagram, there's an applied force acting on box A, but they don't tell me what it is. What other force or forces are acting on box A? Friction and B pushing back on. Gravity is, but it cancels out with normal force, right? But B pushing back on A. So if I'm looking at box A, okay, box A has got a lot going on, right? It's 6.5 kilograms. There's an applied force that I don't know the value of. There's a force of friction that I don't know the value of. Okay? And there's this force that they want me to find, the force of B on A. I don't have enough information to solve this with box A. There's just too much there that I don't know. I could calculate the net force on box A, but that doesn't get me anywhere, right? I don't know any of these forces. Okay? I can't use sum of all forces after m times A for that box because I just don't have enough information. So, box A is out. Box B, on the other hand, has less going on. Okay? It's 8.5 kilograms. How many forces are acting on it? 2. Okay. What's that force? A on B. Okay? That is the force of box A pushing box B. What do I know about that force? Well, that's part of what accelerates it at 2.6. I'm thinking more, how does that relate to box A? Exactly. According to Newton's third law, that force is equal in magnitude, but opposite in direction to the force that B will exert back on A. A is pushing on B with that much force. B has to push back with that much force. So that means if I can calculate that force, I know how big the force they want me to calculate is. Okay? The reactive force going back the other way. Does everyone follow my logic there? Okay? I'm calculating one force because I know it's equal to the force they want. Okay? The other force acting on box B is the force of friction. And the question told me what that was. Okay? The force of friction on box B is 28.3 newtons. All right. What else can I calculate right now for box B? F net. So the net force on box B is going to be 8.5 kilograms times 2.6 meters per second squared. Mass times acceleration. All right, so 8.5 times 2.6. So the net force acting on box B is 22.1 newtons. To the right. Okay? That force, that net force, is the sum of the force of friction and the force of A on B. Since I know 2 out of the 3 of these, I can use sum of all forces to find the one I don't have. Right? So the force of A on B is net force minus the force of friction. So that'll be 22.1 minus negative 28.3. Okay, so the force that A exerts on B is 50.4 newtons to the right. So the force that B exerts on A is 50.4 newtons to the left, actually 50 newtons because there's only 2 significant digits in this question. All right, everyone follow the convoluted reasoning we had to go through to do that? Okay, but again, just like yesterday, the extent of our mathematical computations were multiply 2 numbers together, subtract 2 numbers. Okay, we didn't have to do a lot of calculating to arrive at this answer. We just had to do a lot of thinking to get to this answer. All right, questions on that? Sorry, do you need that down there too? All right, let's try this one. Yep. All right, so this one here, similar, except now it's not two boxes being pushed, it's two logs tied together with a chain being dragged. Okay, we've done a few like this one already. It's a systems question, but it's also got a Newton's third law twist to it. Okay, so give it a read, draw it out, and solve it. All right, so we've got these two logs that are being dragged out, okay, by a team of horses. All right, so we've got log B, which is 250 kilograms, attached to log A, which is 150 kilograms, which is attached to the horses. Okay. So the horses are pulling with a combined force of 2,600 newtons. Okay? And then in part A, they tell us that the force of friction on the system of logs is 2,400 newtons. Right? So to solve part A, I can simplify this diagram, okay, so that it just reads this: 400 kilograms being pulled this way by 2,600 newtons, and this way by 2,400 newtons. Okay, everyone all right with that? So can I calculate my net force right now? Yes. Okay. So F net is 200 newtons forwards. Okay. Now I can calculate my acceleration. F net divided by the mass of the system. So 200, okay, divided by the mass of the system, which is 400. So our acceleration is 0.5 meters per second squared forwards. Right. So part A is pretty easy. That's just a Newton's second law systems question. Okay. Part B is where Newton's third law comes into play. Okay. They're saying the force of friction on log A is 900 newtons. Calculate the force exerted by log B on log A. All right, so this is all about log A. So I should probably draw a free body diagram of which log at this point. A. I have more information about log A. I could solve this with log B just as easily. I just have one more step. Okay? And it's not a hard step, it's just subtraction. Okay? But let's solve it with A first. All right, so I'm going to draw a free body diagram of log A. It's 150 kilograms. It's being pulled by the horses directly this way with 2,600 newtons worth of force. There are 900 newtons worth of friction. And the drag from log B, pulling backwards. Okay, that's the force of B on A. Everybody all right with that? All right, so for this right now, okay, I don't even really need Newton's third law to solve this at this point. I just drew a free body diagram of one of the logs, and now I can solve for the force I don't have. Okay? What do I need to do before I can do that, though? What haven't I calculated for log A yet? Which force? Yeah, net force, right? I haven't calculated the net force on log A yet. I calculated the net force on the system, it was 200 newtons, but that was for all 400 kilograms. I need to know the net force on log A so I can use the sum of all forces to get the force I'm supposed to calculate. So F net on log A is 150 times 0.5. All right, so my net force is 75 newtons forwards. Now that I know that, now I can use the vector sum of all forces. Okay, F net is going to be the force of the horses plus the force of friction plus the force of B on A, which is the force I'm supposed to find. Okay, so now I'm just going to subtract these two over here, and this is what I'll have. 75 minus 2,600 minus negative 900. That's my friction, and it's negative. Okay, that'll give me my force of A on B. All right, so 75 minus 2,600 minus negative 900. Okay, so I'm getting 1.63 times 10 to the 3 newtons backwards as the force that B exerts on A. Everybody okay with what I did there? Yeah? Okay. Just saying, I could also solve this using box B, but I'd have to do one extra calculation. And it's that I have to figure out how much of the total friction that they gave me in part A is acting on log B. Because they told me that 900 newtons of it is acting on log A. So all I have to do is say, all right, if there's 2,400 newtons of total friction in the system, and 900 of it is on the first log, then there must be 1,500 newtons left acting on the other log. Are you okay with my logic? Okay. Then I just go and I draw log B. It's 250 kilograms. What's that force? A pulling on B. Right. Those are the only two forces acting on log B. Okay? There were 3 forces acting on log A, only 2 acting on log B. Okay? So I would calculate the net force, right? 250 times 0.5. Okay, so we got 125 newtons of total net force on log B. Okay, and then we would subtract the force of friction, which we know is 1,500 newtons. Okay, which is again going to give us that 1.63 times 10 to the 3 newtons, okay, forward.
Do you care which way we do it?
Nope, because either one is equally valid. All right, making some sense? So those kind of questions are as complex as Newton's third law gets, okay? Much of the time, Newton's third law is simpler than that. Okay, where one thing pushes on another, the forces are equal, calculate the acceleration of one or the other of the 2 bodies involved. Okay. Now that said, I almost always put a 2-box question on your unit exam. Okay, so going over those examples before your unit exam would be advisable. All right, so I want you guys to try a couple of the ones from the digital workbook here. I'm just going to put them up on the board. I want you to work on those for a little bit, and then see how we're doing after that. Yep. No, tomorrow's will be a Newton's third law. Yeah. But I don't think I'm gonna make it like a 2-box or 3-box kind of question. It'll probably be more like these, which are much easier. All right, so I've only got 4 Newton's third law problems on here, so they won't take you very long, especially since none of them are box A pushes on box B, pushes on box C, pushes on box D, pushes on box W. Yeah, okay. They're all much simpler than that. Okay, so for question number 1, we got these 2 students and they're gonna push against each other. So they're just gonna put their hands up, okay? Put their hands together and they're just gonna push, okay? So student A has a mass of 38 kilograms and during the push is accelerating east at a rate of 0.6 meters per second squared. So mass of A is 38 kilograms. Acceleration of A is 0.6 meters per second squared east. All right, student B is accelerating west, because obviously they have to go the opposite direction, okay, at a rate of, so acceleration of B is 0.75 meters per second squared west. Okay, so we have to find the mass of student B. Is she heavier or lighter than A? She's lighter. her acceleration is greater, so she must have less mass. Okay, so at least we know now, we have some way we can somewhat verify our answer. So here's what we have to realize. The force on A is equal to negative the force on B. Right? That's Newton's third law. Every action has an equal and opposite reaction. That's what it looks like mathematically. So the mass of A times the acceleration of A equals negative mass of B times acceleration of B. I have all of these first ones, MA, AA, and AB, right? I just don't have the mass of student B. So I'm just going to divide both sides, okay, by the acceleration of B, and that'll give me negative the mass of B, but I mean, it doesn't matter here, I'm getting a mass. Mass is an absolute value, you can't have negative mass, okay? So I'm just gonna solve for it, okay, and then I'll have her mass. So we will have 38 times 0.6, okay, divided by 0.75. Okay. So the mass of the other student is 30 kilograms. Any other ones giving us trouble? Okay, keep going. Okay, so while standing on this horizontal frictionless surface, a 45 kilogram student throws a 3 kilogram object to her right. So the mass of the student, 45 kilograms, okay? The mass of the object, 3 kilograms. All right. During the throw, the object was accelerated horizontally through a distance of 0.60 meters. Okay, from rest to a velocity of 9.6 meters per second. This is all information about the object, not the person. Okay? Calculate the velocity of the student when the object is released. Okay, what can I calculate with this information right now? I can calculate the acceleration of the object. Okay? Once I have the acceleration of the object, can I find the force on the object? Yes, I can. Mass times acceleration. Would I then know the force on the student? I would, because they're equal. Okay? And then, since I know the student also starts from rest, okay, I'd be able to solve for the final velocity of the student. Okay? So here's what I'm going to do. I'm going to find acceleration. So acceleration will be Vf squared minus Vi squared over 2d. Okay, so that'll be 9.6 squared minus 0 squared over 2 times 0.6. And that'll give me the acceleration of the object. So 9.6 squared divided by 1.2. All right, so the acceleration of the object is 76.8 meters per second squared, which is big. Really big. But it's a small object, I guess. I might have just made numbers up and got strange numbers. Okay, so there's my acceleration, 76.8 meters per second squared. All right, now that I have that, now I can calculate the force on the object. Okay, mass times acceleration, so 3 times that number. Okay, so 230 newtons is the force that the student exerted on the object. It is also the force the object exerts back on the student. Okay, so now I've got that 230.4. Okay, so now I can calculate the acceleration of the student. Okay, it'll be 230.4 divided by the mass of the student, 45 kilograms. Okay, so their acceleration is 5.12 meters per second squared. All right, so now that I've got that, okay, I have the acceleration of the student. I have the initial velocity of the student. They were at rest. And I don't have anything else, because here's the thing. The student would not have accelerated over the same distance as the object necessarily. But the amount or the time for the acceleration of both would be the same. Because they're only accelerating for as long as the force is being exerted. Can I find out how long this acceleration takes? Then I can use the time, and then I can calculate the final speed of the student. That's my set of steps moving that way. Okay, so I'm going to use the information I calculated about the object to get the time. Okay, so time will just be VF minus VI over A. Okay, and that would be the same for both. So 9.6 divided by the 76.8. All right, so there's my time, 0.125 seconds. Okay, now that I have time, VI is 0, okay, and I have the acceleration of the student, now I can find their final velocity. So VF will equal T times A. Okay. What was it? It was 5.12. Right, 0.64.
So I did it like totally different,
Yeah,
and I
me too.
still got the same answer.
Okay, how'd you do it? Did you use the same distance?
Yeah, I used like t equals d over delta v, and then I calculated a different time, and then I used that to figure out acceleration, then I used that to figure out like the net force, and then I divided by the mass, and then divided by time. I still got the same answer.
Okay, you actually did it the same way I did. Did you use different formulas to get your
And I just
numbers?
got like different answers because I used different formulas. Like I got like different answers for everything except for my final answer.
I got
That's
my
okay.
answer when you did
Yeah.
work.
There's more than one way to skin a cat. Apparently, I've never tried it, but actually that's not true. In university, one of my labs was that we got a cat and we dissected it over the course of the semester. And the first part was we actually had to take the skin off so we could see the muscles underneath. So I have skinned a cat, but only one way. It wasn't alive.
Was it
What type of cat was it?
hard?
I don't know. It was like the SPCA. It's the one they would put down. You know, they would donate them to the university, and then they would be used for labs. Is that sad?
What else are you gonna do? What else are you gonna do with that cat?
They
Non-mandatory.
cremate them.
Tape it to my wall.
I find that using it for science is a lot less weird than keeping it to your wall. It's
It's
just
like
me.
those people that have their pets like the
And we're recording this.